Hi folks, welcome to class 17, the last class before spring break. It's always kind of a celebratory class, so today I thought we'd cover a topic that's just awesome, and that is glaciers and ice sheets. And these obviously tie into climate because glaciers are a function of climate, and they also play a role in things like the ice reflectivity feedback that we talked about on Monday. So glaciers are important, but they're also awesome. So in this video, we'll give you a quick overview of glaciers. Then we'll look at a couple different types of glaciers. And then we'll talk about glacial mass balance. So why are glaciers awesome? Well, for one thing, they are responsible for sculpting much of Earth's topography. We'll see in a second, they're literally rivers of ice that are capable of eroding the landscape, but also depositing a lot of sediment on the landscape. And we find glaciers in every high mountain range in the world. So the Himalaya, which a couple shots here from glaciers in the Himalaya, as well as the Andes and a bunch of other places. So anywhere that mountains get high enough to be cold, that precipitation falls as snow, and they build up their own glaciers that actually start to erode the mountains themselves. And that's been proposed as a fundamental limit on the height of mountain ranges, is that if they get too big, their glaciers also get too big, and they actually start to erode them faster than they can grow. Pretty awesome. So glaciers are also cool because they have a role in climate, and they control sea level. So obviously Earth has a big ice cap at its southern pole. That would be Antarctica. And we got a lot of water locked up there. That's important for controlling sea level, also for controlling reflectivity, as we talked about on Monday. Interestingly, Mars has the same thing. Mars has a huge ice cap at its pole, and its is a little bit dustier than ours, but it has a very similar function of storing a lot of water and CO2 and also reflecting energy back to space. Glaciers are also important in many places as part of the hydrologic cycle. So in western Tibet, here, the Kunlun Mountains, it's a very arid area, and these melting glaciers provide critical water to Tibet and also to parts of China, and very similar situation in parts of the Andes as well. So let's talk a little bit about what glaciers are. Glaciers are rivers of ice. So literally the way they work is that snow falls in the mountains and accumulates up in the high peaks, and under its own weight that snow eventually turns to ice, and that ice starts to actually flow downhill. And obviously we're not familiar with ice flowing, but indeed it will. If there's enough weight over it to create pressure and there's enough of a slope coming down the valley, that ice will deform, kind of like molasses, very slowly, and will actually flow under its own weight, a process called pressure sliding. I slipped in a picture of myself here. The year after I graduated from college, I drove my car up to Alaska and took a look at a lot of different glaciers, and boy, was it an inspiration. And now I'm a geology professor. So if you want to be inspired, go to Alaska and look at some glaciers. All right, so now to get serious. What types of glaciers do we have? So we're going to group these in two different ways. The first way is by morphology. We can think of both ice sheets as well as valley glaciers, and these are very different things. So ice sheets, like Greenland or Antarctica, are humongous. They're several kilometers thick often. They are thousands of kilometers wide often. So they're huge. They cover continents. They cover the scale of continents. And they're slow. They sometimes flow downhill, but often they'll just flow under their own weight. They literally get so thick that the ice starts to flow away from the thickest part of the ice sheet out towards the edges. Again, kind of like a freshly squeezed pile of molasses slowly spreading out across a pancake or a pan. And ice sheets are also driven by latitudinal climate gradients. They accumulate in the north, for example, Arctic Canada, and they'll often flow south towards warmer areas near the equator, or not near, but towards the equator. And often their southern tip will be melting while their northern body is accumulating. And that was, of course, the case in the ancient ice sheets of North America. Now, the other category is valley glaciers. These are glaciers you're more used to thinking of or maybe seeing. This is where snow accumulates in the high mountains and actually flows out through mountain valleys. So very much like a river, these glaciers tend to be smaller. They're often hundreds of meters thick, maybe hundreds of meters wide, and they're fast. They're usually flowing down a much steeper topographic gradient, and so they can come ripping out of mountain valleys. In cases like southeast Alaska, these glaciers can advance tens or even hundreds of meters per year. So they're really coming quickly, and you can see them change from year to year. And these are often driven by elevation gradients. These are driven by the difference in temperature between the high mountains, where the snow accumulates, and flowing down towards warmer, lower elevation areas where the snow melts. Now, we can divide glaciers also, in addition to morphology, we can divide them into thermal categories. And the two thermal types are called temperate and polar. Temperate glaciers tend to occur in warm, wet areas, and they're sustained by very high snowfall, despite the fact that they may also be melting a lot at their tip. So a good example is glaciers in New Zealand. New Zealand is quite warm. It's kind of almost a subtropical area, but it has high mountains that get a lot of snow, something like 2 to 3 meters per year, okay? And so even though the tip of the temperate glacier is melting down here in the very warm lowlands of New Zealand, the upper areas are accumulating snow fast enough that snow turns to ice and flows down, and by the time it melts, more snow has come to replace it. So temperate glaciers tend to have a lot of high throughput of material, and they tend to be sustained by snowfall. Polar glaciers, on the other hand, occur in cold, dry areas. For example, the Taylor Glacier in Antarctica. And they're basically sustained by slow melting. They basically don't melt. It never gets above freezing in Antarctica, so there's no direct melting. The only loss of mass from the glacier is by what's called sublimation, where you go straight from snow or ice into water vapor. So there's basically no melting. But there's also no precipitation in Antarctica. Antarctica gets 0.04 meters per year of precipitation. So, that's something like almost 100 times less than Antarctica gets, or than New Zealand gets. So these polar glaciers are accumulating very slowly, but they stick around because they're also basically not melting at all. So we've alluded to it. Let's look closely at this idea of glacial mass balance now. So, as I've already said, glaciers are rivers of ice, and that ice flows from a zone of accumulation, in this case in the mountains. This will be an alpine glacier example, or a valley glacier example. So we get accumulation in the mountains, the ice flows down towards an ablation area down at the tip. Okay? And the key point is that snow that falls up here and turns to ice literally actually flows over hundreds of years down to the tip of the glacier where it melts out as water. Okay? So this is kind of a steady, ongoing process. So what determines how long a glacier is? Because we know that glaciers can advance sometimes, but they can also retreat during other times of Earth history. So what controls whether those glaciers are advancing or retreating? Well, the first thing to understand is that if you advance your glacier, it means you're growing the volume, right? You have more ice in that glacier. If you're retreating, it means you're shrinking the volume. And we can think of the change in volume as simply being the accumulation minus the ablation. So literally, how much did you put in up here versus how much did you lose down here? Now, if this balance is 0, so the amount lost balances the amount that accumulated, then we can say the glacier is at equilibrium. There's a mass balance, and that would mean there's no change in length. The glacier is stable, it's just going to stay at its regular length. But if climate changes, and let's say we start to increase ablation, for example, global warming hits, and the temperatures down here suddenly get a lot warmer and the summer gets a lot longer, we may end up increasing ablation more than we increase accumulation. So in that case, we'd end up with a negative volume change. The glacier would not be in equilibrium, and it would actually shrink to a smaller glacial size. So as I just said, if we have a positive mass balance, then the glacier will advance. If we have a negative mass balance, the glacier will retreat. But what's pretty cool about this is there's some feedbacks built in here. So let's say the other case now where climate gets colder, for example, and ablation becomes less at the tip, so we get less melting at the tip. That's going to allow the glacier to actually advance further, right? Its mass balance is going to be positive. There's going to be more in than there is out. And so the size is actually going to increase. And the glacier is going to push its nose all the way down to lower elevation. But there's a feedback, which is that the lower elevation it goes, the warmer temperatures it encounters. And so the warmer temperatures it encounters, the more melting there is, and that's eventually going to reduce or eventually increase ablation enough that the glacier will have reached a new equilibrium. Likewise, if it gets abruptly warmer and the glacier starts to retreat, eventually it's going to go back up into a higher elevation area where there's less melting and it's reached a new equilibrium. So there's these kind of feedbacks that regulate, and we call them negative feedbacks, that regulate how far a glacier can advance or how far it can retreat. Now, getting back to polar and temperate glaciers, what's fascinating is that not all glaciers are affected by climate in the same way. And this makes each type of glacier kind of a unique recorder of climate. So for example, polar glaciers are very insensitive to temperature change. Because that glacier is below freezing all year, you know what? If it warms up a couple degrees, that glacier's still not going to melt into Antarctica for the most part. So they're not very sensitive to temperature, but if there was a radical change in precipitation, where we suddenly got a lot wetter in Antarctica, well, those polar glaciers sure would start to grow. Now, in contrast, temperate glaciers are the opposite. They're extremely sensitive to temperature because we saw that the snout of that glacier in New Zealand was sitting in a very warm area. So if it warms up a couple more degrees, then melting's going to get even more intense, and that glacier is going to retreat. And of course, in contrast, these temperate glaciers tend to have a lot of precipitation already, so they're a little less sensitive to precip, and they're a little more sensitive to temperature. And you can see that summarized in this plot here. So on the x-axis, we've got the amount of precipitation coming into the glacier. So these glaciers out here would be very wet, generally temperate glaciers. And then these ones over here would be dry polar glaciers. And then right here it says meters of precipitation required to balance a 1 degree temperature increase. Okay? So if we increase temp by 1 degree, then we would need to have roughly an extra 0.3 to 0.5 meters of additional precipitation in order to balance that out. But for some of these wetter glaciers, if we have a 1 degree temp increase, we'd need to increase by 1 or more meters of precipitation in order to balance that out. So this shows the differing sensitivity to precipitation for different types of glaciers. So I'll close this lecture with a little thought point, which is that this picture shows a glacial moraine in the eastern Sierra Nevada near Bishop, California. And the glacier today is way back up here, maybe almost gone. And this moraine is material that was pushed up when that glacier advanced all the way onto the valley floor. And it's now melted back miles, literally 4, 5, 6 miles it's melted back. And so this is an example of how the changing climate allows glaciers to have these crazy advances and then retreat back. And we know from dating the age of this glacial moraine that this glacier was last down in the valley around 18,000 years ago. And one of the questions from a paleoclimate perspective is what actually allowed the glacier to advance down that far? And in this case, we know it was both colder but also significantly wetter during the last glacial maximum about 18,000 years ago. But this particular glacier was very sensitive temperature, so as we warmed over the last 15,000 years, it has retreated way back up its valley. So in summary, we introduced glaciers, we looked at different morphological and temperature definitions of glaciers, and then we talked about glacial mass balance. I'll leave you with a couple concept questions, a link to the quiz, and I'll see you for the next video on glacial landforms.